In this video, we'll be looking at related rates in revolving around the concept of the volume of a cube. Now, this particular question reads, the edges of a cube are contracting. Contracting implies that they're shrinking. Shrinking implies that this rate provided would be negative. So the edges of a cube are contracting at a rate of 3 centimeters per second. How fast is the volume of the cube changing when each edge is 10 centimeters? So again, logically, we should have a concept of us having a cube, this cube having a volume, okay, and in terms of this, each one of these lengths is simply x. That's what we're going to call it here, is x. Okay, if that length is x, then this length is also x, and then this length is also x in the front here. Again, because a cube is nothing more than side times side times side for the volume. So we know that this formula, volume equals x cubed, is the volume formula that we're going to work with. Also notice that if it helps, we should identify some pieces of information that we know. I know that I'm going to go ahead and have x equals, I'm going to have v equals, I'm going to have dx equals, dx dt equals, and I'm going to have dv dt equals. Now, I'm going to write all this down in this form because the two variables that I have in this problem are v and x. And they could be changing at different rates, so I'm going to write those values down as well, dx dt and dv dt. When reading through the question, let's fill in the information we're given. So the edge of the cube are contracting at a rate of 3 centimeters per second. Again, contracting, and the edge implies dx dt, the rate of change, is a negative 3. And I'm going to go ahead and use the units, centimeters per second. In this case, I'm going to go ahead and continue reading. The question is how fast is the volume of the cube changing? So this is what I'm looking for, is dv dt. How fast is the volume changing over time when each edge is 10 centimeters? Now you'll notice in this particular question, I'm not given volume, but I'm not so sure that I need to find out what that volume is. What I'm always going to do is, after I've gotten all this information written down, I'm going to get a formula that relates the rates. Again, it relates the rate of volume in respect to the rate of the edge of the cube changing. So my next step is to take the derivative of both sides in respect to t. Again, taking the derivative in respect to t on both sides. This side over here will just simply be dv dt. This side over here, again, what's the derivative of something cubed? Well, it's 3 times that something squared. Again, bring down the 3, subtract 1 from the power, so 3 times that something squared. And then don't forget, we have to take the derivative of the inside. If this was d dx, then that would just be 1, because it would be d of x, d dx. But since it's d dt of x, that means we're going to have dx dt. Since those two variables are different, the variable that I'm taking the derivative in respect to and the variable that I'm taking the derivative of are different, I have to have that dx dt there. So now I have this little formula here. Now again, remember, we were looking for what is dv dt. Given my dx, my length of the edges are contracting by 3 centimeters per second, and then my actual edge that I want it to be is 10 centimeters. I'm going to plug the 10 centimeters in for x, giving me 3 10 squared, and I'm going to plug in negative 3 for dx dt, negative 3. Now when I go ahead and evaluate this looks like it's going to be, again, 100 times negative 9, so 900. And now what is the unit of measurement on volume, and specifically the rate of volume over time? Well, the edge unit is centimeters. The volume unit should be centimeters cubed then, because it's centimeters times centimeters times centimeters. And then the time unit won't change. So this is going to be negative 900 centimeters cubed per second. Now let's talk about that this makes sense. Okay, if this is my final answer, does it make sense? Well, if each edge is contracting by a negative 3 centimeters per second, meaning in this image over here, rather than having this cube not changing at all, what it's going to be doing is it's going to be shrinking. So if I draw a smaller cube inside of that cube right in this corner here, you'll notice, okay, it's changing by a large amount. Here is the overall cube. This is the new cube in here. And each length changes by a negative 3. It decreases. The rate at which the volume should change should also decrease. Again, notice the volume in the large cube is a lot larger than the volume in the small cube. So again, if I have a decrease in one of the lengths, which will decrease all 3 of the lengths, I will then have the volume decreasing by a much larger amount. This answer then makes sense, and therefore this should be our final answer.